where U lies in this space. Okay? That's simply saying, another way of saying this is that U is both the subsolution and the supersolution, because when you take, if you take minus U, that's U, then this is essentially the complement of the upper cone, and that's what you mean by a supersolution. Okay. Now, I want to say a little bit about log convex domains. So suppose you start with a bounded domain in Cn. This boundary is smooth. Then I say that the boundary is strictly log convex if every point has a defining function, which is strictly log convex. Now, defining function is simply you take the point and you take a neighborhood of the point and a smooth function, which is zero on the boundary and has non-vanishing outward-pointing gradient at all points. So it's negative inside, positive outside. And to say that it's strictly Fourier type-harmonic simply means that its trace on every Lagrangian plane is strictly positive. Okay? So, but this can be also characterized in terms of the intrinsic geometry of the domain. Namely, you take the second fundamental form of the domain with respect to the interior normal, and the interior normal, and you ask that the trace of the second fundamental form on every tangent Lagrangian plane is strictly greater than or equal to zero. So this is something which is, a property of the geometry of the boundary of this domain. Okay. So given all that, we can do the following. Given any domain in Cn bounded with a strictly convex boundary, smooth boundary which is strictly log convex, then for every continuous function on the boundary, there exists a unique function continuous on the closed domain with a property she'll expect is log harmonic in the interior and equals D on the boundary. Okay, so existence and uniqueness hold. Okay, so this means we have lots of these things locally. Any convex domain is log convex. Okay, so the question is there a polynomial differential operator whose solutions are log harmonic? So is this actually given by some polynomial operator? And it's not always true, even in these geometric cases. You can always write down some sort of operator, but the operator isn't given by a polynomial. You can't differentiate it. So it would be nice if this was true. And so I want to go back to this thing that we did before. So you take the 2n by 2n symmetric matrices and decompose them under un. So the first thing that happens is it decomposes into Hermitian symmetric and Hermitian skew symmetric parts. And then the Hermitian symmetric parts themselves decompose into multiples of the identity and the traceless symmetric parts. So if you start with an A, which is a 2n by 2n symmetric matrix, it first of all decomposes, as I said before, into this piece which commutes with A and that which anti-commutes with A. And then the one that commutes with A can be written as the appropriate multiple of the identity, namely the trace over 2n, and then the Hermitian symmetric part minus that, which is the traceless part. Okay, now this is a complete reduction under the unitary group. And the basic fact is that the log analysis, everything that I'm going to talk about, is completely independent of the traceless Hermitian symmetric part. It plays no role. So this is easy to see, but let me prove it for you. So suppose I have a 2n by 2n symmetric matrix, which is symmetric and of trace zero. Symmetric and of trace zero. And I take a Lagrangian plane, W. I can choose an orthonormal basis for W, E1 through En, and then the trace of E on W is simply the sum of E of phi to EK inner product of EK, from 1 to N. But multiplication by I is an isometry here, so I can replace E, capital E, small e, EK on the inner product with EK by putting J's in front of them, right? J is an isometry. So I can do that, and then divide by a half, and I get the same thing. But now, because this guy is a symmetric part, here it is. J commutes with E, so it comes down here. I can put the J on the inside. Now you're looking at the trace. And that is zero, because it was in the trace zero part. So if you take these guys and take the trace on Lagrangian planes, this part is always zero. It plays no role. So this is kind of interesting. If you go back to the complex Legendre equation, everything, it's all about the Hermitian symmetric part. It's exactly, and if you look at the skew symmetric part as I've defined it, it plays no role because its trace on every complex line is zero. Right? The skew symmetric part is trace on every complex line is zero. So now, in our case, if you look at what I want to call the Lagrangian part, which is the part that's a multiple of the identity plus the skew, this plays a central role in log analysis and in the Lagrangian momentum theory equation, but the traceless Hermitian part is invisible to this theory. So there's a kind of duality here between the complex motion theory equation and what I'm going to discuss as the Lagrangian motion theory equation. So what is the Lagrangian motion theory equation? Well, suppose I have something which is Hermitian skew, that is, it anti-commutes with J. Okay. So if I have an eigenvector E with eigenvalue lambda, then JE is also an eigenvalue with eigenvalue minus lambda. So that is to say that the eigenvalues for the skew symmetric part appear in plus and minus pairs. So this symmetric matrix looks like this. The eigenvalues are lambda 1 minus lambda 1 times lambda n minus lambda n. And it's really hard to, you can't really determine which is which, but so if you want to make this more canonical, you can just order this so that all the lambdas are greater than or equal to 0. Okay? And you can see that if we make this assumption that all the lambdas are greater than or equal to 0, that the trace of this skew symmetric part on any Lagrangian plane is greater than or equal to this maximal negative value, which is minus lambda 1 through lambda n. Okay? So now suppose we have a 2n by 2n symmetric matrix, and I have a Lagrangian plane W. Then if I take the trace of A on W, as I've just shown you, the Hermitian trace, the symmetric traceless part goes away, and that's just the trace of this Lagrangian on W. And now the trace is linear, so the Lagrangian part comes out, or the trace of the identity on this is n, so it comes out as the trace of A over 2. And then I'm left with the trace of the skew symmetric part, which I've just pointed out to you is greater than or equal to mu is now in M over 2 minus the sum of positive eigenvalues. So here's where lambda 1 through lambda n are the non-negative eigenvalues of the skew symmetric part. Okay, so this is all fairly straightforward, and so now what are you going to do with it? so I now see that I always have this inequality, as I've just said, and so that means that the trace of A restricted to any Lagrangian plane is greater than or equal to 0, even only if this quantity, the trace over 2 minus the sum of the positive eigenvalues of the skew symmetric part is greater than or equal to 0. Okay? So let's consider the following operator. I can't really differentiate between, there's no way of sort of finding out where the positive and negative eigenvalues are in some sense. So what you want to do is to go over all of them. So I'm going to take a product. This mu is always fixed. Of mu plus and minus lambda 1 up to plus and minus lambda n, and I go through all the signs. Right? So that's 2 to the n factors, right? Linear factors here.